Hello, I'm Graham Greenwood-Sewell, the Managing Director of Corrocoat. I have been involved with the development and manufacture of high-performance coatings for over 25 years. Today I'd like to discuss accelerated testing. Performance testing on coatings has increased dramatically over the past 10 years, with many companies using test regimes such as NOSOC M501 etc. to validate coatings they use or to approve new coatings. Whilst it is certainly true that such test programs can be used to identify weak coating systems, a fundamental question is how to separate and quantify the relative performance of good or excellent coating systems and how to approve coating materials for aggressive service applications. Time is often the enemy. We need answers this week or this month, so how do we achieve this? One solution may be accelerated testing, or is it? For any test work to be accurate and relevant, it must be appropriate for the service duty. Unfortunately, obtaining reliable data may require extended test durations. It can be expensive, or it may be that we simply do not have the time to wait for the information. One approach, often used, is to accelerate testing, often by increasing the test temperature above that which the coating will see in service. Unfortunately, the molecular structure of coatings changes as the temperature increases, especially as the glass transition temperature and thermal softening point is approached. These values vary widely on differing coating systems, and other effects such as the cold wall performance and permeability are also dramatically affected by increasing temperature. The net result is that if a coating is designed for use in a particular environment of 50 degrees C, testing at 75 degrees C will not give us reliable data on the long-term performance at 50 degrees C. It will simply tell us how the coating performs at 75 degrees C for the test duration. Another common error is to increase the severity of the test environment by increasing the chemical concentrations. Again, the correlation between results obtained by this approach is at best tenuous. If, for example, we wish to test the resistance of a coating in a storage application of a particular acid at a concentration of 20%, realistic immersion testing may take months. Testing at a concentration of 40% for half the time cannot give us the data we need. The coating may or may not pass this test, but it merely tells us how the coating performs against the 40% acid over the test duration. Changing the test environment is surprisingly common for testing within the oil industry, often due to the difficulty in obtaining and shipping even small samples of crude oil. For best results, it is always good practice to test the actual oil in question. Let us look at this test regime. The client insisted on testing using a blend of hydrocarbons, including a low molecular weight aromatic substituted for the oil. The coating was tested in an autoclave for explosive decompression and failed. Whilst it was true that a fraction of a percent of the low molecular weight aromatic would have been present within the oil, this test environment bore little resemblance to that of the process for which the coating was selected. On the basis of this test work, the client chose an expensive metallurgical solution rather than the coating. Yet when Corrocoat repeated this work, simply replacing the hydrocarbon phase with an equivalent crude oil containing a few percent of the aromatic, the same coating performed perfectly and passed the test. A cost-effective coating was overlooked, resulting in significant additional expense on the project due to the inappropriate test regime. I have highlighted that any test must be representative of the environment for which the coating will be in service, but there are some test protocols which have been shown to offer better data regarding the relative performance of coatings. These include cold wall testing, cathodic despondment testing and water vapour permeability. Cathodic despondment testing has already been highlighted in a previous Corrocoat video. This test is one of the best methods of measuring immersed adhesive strength and the resistance to undercutting from a damaged site. The resistance to moisture vapour permeation is critical for long-term performance of any coating system. Poor resistance to moisture vapour transmission results in early breakdown of the coating system and rapid failure in service. The most common test evaluation method being ASTM D1653. Chemical immersion testing is often carried out using fully encapsulated sample plates or test rods. Unfortunately, whilst the chemicals present may match the process conditions, this type of test is often not representative of the environment, as in service the coating will often also have a thermal gradient across it. The temperature gradient may allow for the condensation of water vapour at the substrate or within the coating, the mechanism known as the cold wall effect. Testing for the cold wall effect requires test cells such as this pressure cell, which can be used at test temperatures up to 200 degrees C. Plates are coated with the coating in question and immersed in the process environment at the required temperature and pressure. The cell may be cooled externally by air or water at the required temperature. Cold wall testing, cathodic despondent testing and water vapour permeability will give a good indication of the coating's performance. All of the tests discussed during this presentation will at best give you data on the likely performance of the coating in a particular environment, and long-term testing cannot be avoided. However, if you want accurate data on a particular service duty, there is no better way than to seek track records and case studies for that coating in the same or similar environments. Thank you for your interest.